Here we are. So now the recording started. Welcome everybody. We are here to talk about AI for emergencies. But first, a few words about my team, 510. Well, we take our name from the total surface of Earth, 510 million square kilometers. And it's because we aim to help every national society in need everywhere. And we are a data team, so we just took the number. Our purpose is to improve the speed, quality, and cost effectiveness of humanitarian aid by using and creating data and digital products. It is a bit of a word salad, but the sense is exactly how can we use data and digital to improve the work that we do. And this fits very much with what we're talking about today. This is the outline of this tutorial. So I'm going to start with a bit of motivation. So why are we talking about using AI, or more concretely speaking, why are we talking about automation? So automating certain tasks that we do using AI. We are going to talk about mapping and damage assessments. So I want to clarify exactly what do I mean with this, and specifically within the scope of this tutorial, and what I don't mean with that, since these terms might be used differently by different people. And finally, I'm gonna show you how to do it. It's gonna be a hands-on tutorial. There is a bit of setup needed. I'm gonna walk through every step, so feel free to do it along with me, or otherwise you can use this tutorial afterwards. I'm gonna share the slides later. There is a lot of documentation on GitHub, so you can you can also do it at another time, but you should have all the information needed to get started with this by yourself. So let's start with the why. So why are we talking about automation? We are the Red Cross, so let's start from the most important use case for us, which is a disaster. Let's take a large-scale disaster, like a hurricane, which, as you see from this picture, it can affect a very large area. And correspondingly, the scale of the emergency response will have to match the scale of the disaster. Now, when a disaster like this, like a hurricane, happen, this is the kind of scenario that you face afterwards. And this is a drone image taken in St. Martin after 2017. There was a hurricane there, and this is the kind of scenario that we often face. So destroyed buildings, debris, and we need to assess the situation. We need to understand what is the scale of the damage, and what are the needs of the affected people? That's usually the first questions that we ask. Now, if the affected area is a town like the one that you see in this picture, well, it is relatively simple to do. But now, as I mentioned earlier, if the scale of the disaster is large, for instance, here you see the entire island of St. Martin, and if you know that the entire island has been hit by the hurricane, you might wonder, okay, where do we go next? We have limited resources, limited personnel, limited time. So where do we start with our assessments, right? Maybe traveling from one side to the other of the island can take hours. So you would like to have a quick overview without necessarily going in all these places. Prioritizing, especially when the scale of the disaster is large and the resources are limited, it is very important to then prioritize intervention areas. So where to go first, because this also means reaching the people that need aid the most. It's about prioritization. Now, so after a disaster, then what do we need to know? Where are the people in need, concretely speaking? And how bad is the situation? I just explained. So the scale of the damage. Of course, we already do it. And the way we do it now, of course, is first of all, by going to the field and taking a survey to understand exactly what is the damage, where are the people in need, and what is the scale of the damage, and what do they need. And this is often impossible, either because the roads are not usable, like you see in these pictures, or maybe the roads are usable, but the area is so large that it would take weeks or months to follow, to cover all the affected area. So it might be, in terms of time, it would be just too slow to do it in the field. Another thing that you can do, of course, is to use satellite imagery, and this has already been used. And nowadays, it's mostly done manually. So people take a satellite image and then manually label, so to speak, the damage in the buildings. They say, okay, this was destroyed, this was not. And there are many agencies that do that. I think the most known one is UNOSAT. You see here a map that they produced after the explosion in Beirut in August 2020. And this is a service that these agencies already provide, and it's being used by many humanitarian actors. But this can also be too slow. Now, in the case of Beirut, probably was the ideal use case because the explosion was really limited to an area of the city. But now imagine a big disaster. To do it by hand can also be too slow. If affected area is, I don't know, half of the Philippines, for instance. So the reason, like all of these basically is just to lead us to the reason behind automation. So automation is about speed and availability, right? In all these cases that I mentioned, it was either too slow to do these assessments otherwise, or it was not possible for any other reason. Now, if we talk about speed, to give you more concrete numbers, machine like automation through computers and models, suitable models, can speed up things by a lot. If we talk about mapping, well, one computer can easily map about 1,000 square kilometers per hour, again, to give you order of magnitude. Whereas in typical tasks in OpenStreetMap, these are many humans manually labeling the images. It usually takes, okay, depends on the disaster, but it usually takes on average not more than 100 square kilometer per hour. So if you can automate the procedure, you get a factor of 10 in speed. You are 10 times faster than with any other platform, without taking into account all the time to set up a tasks in OpenStreetMap and in Hot, etc., etc. The same with damage assessment, then the gain in time is even faster. So since now it's just about classifying images, this from a computer perspective is even quicker to do. So a computer can easily classify 10,000 buildings per hour in terms of damage. Whereas these agencies, like I mentioned, UNOSAT, that they do these manual assessments on satellite images, well, they usually they're not faster than 100 buildings per hour per person. So here, what you gain in speed is a factor of 100. You're 100 times faster if you can automate the procedure. Again, depending on your use case, the manual version can be absolutely fine. But if you're dealing with large-scale disasters, think about Dorian in 2019 or Typhoon Haiyan in 2013, which really affected, different countries, entire countries in some cases. Like the Bahamas, to do it by hand is simply unfeasible by anyone. So automation is the only way that we can actually provide data with the speed that is needed for emergency operations, which usually cannot afford to wait for weeks or months. Of course, the speed that I mentioned here is for one computer, right? But machines are not different than humans. So machines can work in parallel. You can take a bunch of data, you can assign it to different computers. Each computer can run the same model, and then the output can be put together, right? So this speed can even be increased if you have many computers at your disposal. Nowadays, with the cloud technology, we are in the position in which it's very easy to rent computers for a limited amount of time. You can rent it from your cloud provider. I'm talking about AWS, Microsoft Azure, Google. You can rent machines only to execute a specific task and only pay for what you use them for. And this basically tells you that you can go as fast as you can pay for. If you can rent more machines, you will go faster. We, for instance, implemented a solution in Azure using what is called Azure Batch. It's just a specific implementation in Azure of what is usually called distributed computing, which does exactly this, how to split a workload among multiple computers and make sure that it is as fast as possible. You can check the repository there at this link to see concretely how this can work. Now, if you have a cluster of computers at your disposal, then, as I mentioned, you can be super quick. For instance, using this solution that I just discussed, we can do mapping and damage classification on about 12,000 square kilometers. This was a real case using satellite images from the Philippines before and after Typhoon Mangkhut in 2018. And using 26 computers on Azure, just a reasonable number, we can basically do everything in 1 hour, 1.2 hours, paying 24 euros. Again, to give you a concrete idea of the time and the costs. You can go quite fast without spending too much. So it's, automation, that's what gives you. Let's go in now in the specifics, okay? I think the argument, I hope it was clear enough. Maybe it's a good time maybe to stop and ask if there are questions. Something is not clear. Okay, it seems not, so I will just continue. Now we'll move into the specific use cases that we're discussing today, which is mapping and later damage assessment. Let's start with mapping. I hear Ibrahim. You have a question? Okay. So with mapping, we mean detection of buildings in satellite images. In particular, the scope of this is really emergency response operations, okay? So how can we quickly map vast areas which have not been mapped before to know where people live, to have this kind of, to enable this kind of prioritization that I discussed before. It's really meant to be complementary to OpenStreetMap or any other kind of mapping data that you might have, okay? In case you're working on your emergency and the OpenStreetMap is not complete enough or is not necessarily up to date. Now, it is not meant to replace OpenStreetMap. This is very important because when available, OpenStreetMap is usually of higher quality because many humans, there is always a mapper and a validator, so the end result is usually of higher quality that you can get with any kind of AI model nowadays. Doesn't mean you will see the concrete output in a minute, but let me tell you, it is usually of higher quality. So it's not to replace OpenStreetMap. And also it's not meant to replace any other map product. So if you get data from governments or whoever about the settlements in the area where the emergency is taking place, use them because this is not meant to replace them. It is just a complementary tool in the emergency response. Concretely speaking, what does it mean, automated mapping? This is the workflow, very simply. I take a satellite image, optical, so in the red, green, and blue bands, high resolution, about 0.5 meters per pixel or less. I take this image, I give it to a computer. There is a computer model behind, and it gives me as output the location of buildings in the image, which you see here on the right-hand side as the black spots in the image. Those are the buildings as they are detected by the model. So this is what I mean with automated mapping. And then we can use the location of these buildings to produce maps or usually maps. That's what operationally what people ask for during emergencies. But you can also use this to make estimates on the number of buildings in the affected area, for instance, so the number of people, etc. Yes, Georgios? I cannot hear you. Do others hear Georgios? I see your microphone is on, but I cannot hear you. Maybe if you can write your question in the chat. Thank you, guys. So I'm not the only one. It seems that it's on your side. Yeah, no problem. Just type it in the chat. Maybe in the meanwhile, Sulaiman.
Yeah, thank you. Just a quick question. Is there an estimation on accuracy of using automated mapping? Like out of 100, what is the percentage of accuracy comparing to manual mapping? So thank you.
Good question. It's the next slide. So we'll get there in a second. But good question. Yeah, okay. While we wait for Georgios to solve his problem, I suggest we move on. So yeah, this is what I mean with automated mapping, detecting buildings in satellite images. Model performance, to get back to this question. So we trained the model, for those of you who are familiar with machine learning, this means that the model learned to recognize buildings by looking at many different examples. And we gave the model examples from basically all over the world. Well, not exactly all over, but different continents. This is a large data set of almost 1 million buildings in 4 different continents. To try to ensure that the model had seen examples from a sufficient variety of places, not to be biased too much towards specific locations. And in this data set, the performance we saw is that about 10% of the buildings are missed or misplaced. So again, it's not perfect. It is not meant to be perfect, but I would say a 90% accuracy is good enough if you need to have a quick overview of where are the settlements, where people live, and to make quick estimates on the number of people. I think this is good enough, at least in my experience, in emergency response, seeing the kind of the approximations that are usually needed to be done when information is limited. So we think this is usually good enough. Now, in real life, of course, things can go differently. And this is something important to realize. So performance might be lower depending on the satellite images that you use. For instance, if in your area, the buildings, let's take the first image on the left. You see here that the buildings have the roofs of the buildings have almost the same color as the ground behind those buildings. Now, even for a human in this picture, it's a bit hard to distinguish what is the building and what is not, right? Because everything is more or less the same color. This is also confusing for the model. So if your satellite images look like this, well, you can expect reasonably that the performance will be a bit lower. Weather conditions are also important. Now, if, for instance, in the image in the middle, you see there is smoke coming out of a place, there is probably something on fire. And of course, we will not see buildings behind a cloud of smoke. And there is nothing we can do about it, at least with optical images, you will never see behind the clouds or smoke. So if the images are covered with clouds, you will not see anything. That's the model doesn't do magic. And the same with angle. So you see in the last picture on the right, you see a satellite image of a city taken with a wide angle. I'm talking about angle between the satellite and the surface of Earth. If the angle is much bigger than 0, then you have this kind of you see this kind of effects. You have the shadows of the buildings. You have the perspective on the buildings. So yeah, the model is likely to get confused by a picture like this. All of these are small factors that may actually affect negatively performance. So always check that the quality of your satellite images is good enough. It doesn't have these obvious problems. We move to the next task. Or maybe are there questions on this before I move on? I don't know I didn't want to go into the specifics. I don't know how technical is the audience here, but I want to give you a gist of what does it mean to have a good satellite image to this. Okay, there are no questions. Let's move to damage assessment. And let's try to define again, what do we mean with damage assessment, at least in the context of this talk. So damage assessment means classify damage to buildings. So for each building, you want to say, is it intact? Is it partially damaged? Is it totally damaged? Is it completely destroyed? It is meant to be used again in emergency response operation. So quickly assess building damage over vast areas to know the scale of the problem and provide the first estimates of, for instance, the number of destroyed buildings, the number of displaced people. It is very useful since you can do this very quickly with AI, with these models. I would say it's very useful in the first days after the disaster, when these kind of estimates are usually hard to find or are very, they usually come from educated guesses, but they're not really evidence-based. So in the very first days after the disaster, it's usually useful to have this kind of quick assessments. And of course, it is meant to be complementary to other satellite-based damage assessments, if they're available. So if UNOSAT or other agencies are doing this by hand, of course, this is meant to be complementary to that, not to replace anything. And most importantly, when it comes to damage assessments, it is not meant to replace field-based assessments. As the emergency operation moves on and you pass from, let's say, immediate response to, let's say, a later phase of the response, so rebuilding or helping people to rebuild, then the kind of damage assessment that you need is usually very detailed, and you cannot get there from satellites, right? From satellites, you will only see the damage from the top, from the roof. So you get a sense of if the building is badly damaged or not, but you don't get the details, and you will never be able to get the details. So these damage assessments, as time moves forward in the operation, might need to be very detailed, and this tool will not be useful anymore for this kind of detailed analysis, if that's what you want to do. So for that, you will really need the field assessment, probably with an engineer. So again, this is not replacing that. We will always need to do that at some point. But in the first days after the disaster, this can be useful to, as I mentioned, to give quick numbers. So again, to simplify the workflow, damage assessment means to take as an input a satellite images before and after the disaster, and the building locations. So what we produced in the previous step with the automated mapping. And then there is a computer, there's computer model, and the output would be the building damage. So for each building, it will tell you, okay, it is badly damaged or not. For instance, in this picture, you see in red would be the damaged buildings, and in green would be the non-damaged buildings. Okay? So that's concretely what this model does. Classifies damage per building. If we talk about performance, again, we use the same data set, which was also labeled with damage per building, so we can train the same a different model on the same data set. And in terms of performance, when it comes to classifying damage, performance is a bit lower than when it comes to mapping. We saw that about 15 to 30% of the building can be misclassified, depending on the disaster. So this is the level of accuracy that we get at the moment. Of course, it's a work in progress and it's open source, so everyone can contribute with their own models. We hope to improve this in the future, but that's what we have at the moment. Since we are trying to improve performance, we did a series of dedicated studies on how do we expect the model to perform on a new disaster that have never been seen before, that the model has not seen any data before, and how do certain characteristics of the type of disaster, the geographical location, etc., how does this influence performance? We did a number of studies on that, which have been recently published in an academic paper. So I encourage you to go and check it out, because it will give you a very detailed overview of how do you expect this model to perform in different types of disasters, in different locations, etc. So yeah, just to give you more detailed, better detailed overview of the performance. But the top line is expect something between 15 and 30%, let's say, mistakes in the classification. So now we are moving to the actual tutorial. Again, I'm going to show you a couple of slides, and then I'm actually moving towards a terminal where I will actually run these models live with you so that you can see actually how it is done. And then we will have a look at the output together. Again, feel free to do it yourself if you have the time, the resources, and the energy. Otherwise, I will share the slides and the video afterwards, so you can, try to do it another time by yourself. The use case of today is Hurricane Dorian. I don't know if any of you has been involved in that operation. Hands up if you've been. No. Okay, no one was involved there. Too bad. I was hoping to get some field experience in this. But anyway, I took Hurricane Dorian as an example of how we can use these tools in real emergency operations. I took one city, Marsh Harbor. It's about 50 square kilometers. And I took 2 satellite images before and after the disaster. That was in 2019. And we're going to use this with the models that I'm talking about to do building detection and damage classification. And this is real data that Maxar released on their website, as they do often with major disasters. So you can reproduce everything by yourself by getting the images at this website here that I write on the bottom. The code that we're going to use is ADA collection. ADA stands for Automated Damage Assessment. It's code, it's on GitHub, it's open source. You can get it there. If you're familiar with Docker, Docker is just a software to take a piece of code and make it executable on any machine, because it copies automatically all the configuration files or the things that you need to install. So it's a way to make code very portable among many machines, different machines. So it's also Dockerized, so you can directly get the code using Docker if you're familiar with the technology. But everything is there. Before starting, now this is a tutorial, so we're going to do it anyway. But in real life, I just want to give you a warning. Before doing any of these, check if it's necessary and possible. Okay? In real emergencies, I would always start with a review of alternative secondary data sources. So other agencies that might have done this. So is OpenStreetMap detailed enough? So do we really need to do building detection, or maybe OpenStreetMap is good enough? Is UNOSAT doing the manual damage assessment? Have they already released it or not? So check if alternatives exist. But if these are insufficient because of time pressure or whatever, or because the area is too large and they don't cover it entirely, then it makes sense to use these tools. We need satellite images, so check the quality of the images for all the things that I mentioned earlier, if they're covered in clouds or not. And check if the images are recent enough. If you take images from years ago, it's better to ask to a local person, look, are these, do we see all the stuff that we need to see here, or are we missing, for instance, half of the city because it developed in the last couple of months, for instance. So it's important to check with a local person about the recency of the images. Good tip. If we want to do it, well, the first step is to get a machine set up, where the models that I talked about so far are neural networks, or also deep learning. You probably heard the buzzword. So to train and execute neural networks, it is much more efficient to do it on a GPU. They're just much faster. So since this is all about speed, let's use a computer with a GPU. Otherwise, we lose we lose on the main reason for this, which is speed. So we need a computer with a GPU. You can have your own if you have locally on your office, but we can also rent it from a cloud provider. It is actually the solution that I would suggest nowadays. It's much cheaper if you only need to do this a couple of times to rent a computer from Azure, AWS, Google, or any other cloud provider that you might use. For instance, since we use Microsoft Azure, I'm not sponsored by Microsoft. I'm just sharing personal experience with the tools that I use. Since we're using Azure, this is what you need to do. It's very simple. In a few clicks, you can get a machine with a GPU. You also have different choices in the type of image, depending on the speed that you want. These NC6, NC12, NC24, these are simply different types of machines with different capabilities. So with 1, 2, or 4 GPUs respectively. And depending how fast you want to go, you can choose a machine or another. Of course, the NC24 is more expensive than NC6, so there's a bit of cost benefit analysis, but yeah, there's a lot of choice. And also with other cloud providers, they always provide a couple of choices on that. Now, assuming that we have a computer with a GPU, then we need to, first of all, install the GPU drivers. That's a not very interesting step, but very necessary. So install the drivers for the NVIDIA GPU and CUDA. That's the NVIDIA package to run neural networks on GPUs. Just a few commands, very simple, but get it done. Now, I'm not going to do it by myself now because it takes time and yeah, there's nothing to learn here, but check that the drivers are installed. Get the code. I mentioned that the code that we're going to use today is ADA collection. You can get it with Docker. That's the easiest. Just install Docker and get the image and run a container with that image. Now, if you're not familiar, these are just buzzwords, but they just simply mean that you take the code and you make like a little environment within your computer where this code is running and everything goes as we want it to go. And you don't need to install anything else. Everything is set up automatically. You can also follow the manual setup. Now, this presentation has links, hyperlinks attached. I will send it later. And this points to the GitHub repositories where we have all the instructions on how to install this stuff, how to run it, etc. So yeah, we don't need to go through the details here. But yeah, you can always go on GitHub and check. They are the same instructions, even better explained. If you want to use our models, the models that we developed at 510 Netherlands Red Cross, and that the models whose performance I discussed earlier, you need to download them. Again, they're all openly available on GitHub and put them in your workspace or wherever you're working. Please interrupt me if something doesn't make sense, okay? I'm just going through the list of steps, but if something is not clear, or if you say, why are we doing this, please stop me, okay? Step 4, we need satellite images, okay? That's what the models run on. Now, if your disaster is already on Maxar Open Data, that's a website where they openly put satellite images, then you can download them automatically with a simple command that we, so that's simply a script that we make executable within this piece of code. It automatically downloads all the disaster images from Maxar and puts them in a folder, which I call images. So everything is just one command line. Otherwise, if you want to use your own satellite images, of course, you need to get them from wherever you want to get them and put them into folders. Let's call it pre-event and post-event for pre-disaster images and for post-disaster images. So before and after the disaster, respectively. Okay, that's what we need. So at the end of this setup, just to double check, that's how your workspace should look like. So you have a folder, a directory in your computer. There are the two models. There is the pre-trained building detection model, the pre-trained building damage classification model, and there are the images, the satellite images, before and after the disaster. That's all that you need. The rest is in the code. So we're ready to start running the models. And the first step will be about mapping, so detecting buildings in the satellite image. Again, link to the repository where there are all the instructions on how to do it step by step. Today, I'm just going to show you how to do it live, so to speak. So I already uploaded in my machine the satellite image that you see on the left. Yes, and I'm simply gonna run the model on these machines to detect the buildings. So now you should still see my screen, right? Please shut out if you don't. Now, I'm now showing you a terminal. It's connected to a machine. It's called NC24. It's this GPU-enabled machine that Azure provides. And I've put all the images that we need in this folder, data lake storage, Hurricane Dorian tutorial. There should be images. Now I'm inside a directory which is called images. I have my pre-event and post-event. In pre-event, I have one satellite images, which is what I showed you earlier in the presentation. And the same in the post-event, I have another satellite image post-event of the same area. So that's all the input that I need. Now what I'm going to do is now run the building detection model on this. And it's simply one command in the terminal, so it's relatively easy to do. We just need to pass a bunch of stuff to it. ABD, that stands for Automatic Building Detection. It's just the name of how we call the framework. We're going to pass the predict command. And it's a config file that we have on data config, right? Yes. This is simply to tell it how to run the model, but it's just a standard configuration file. We need to pass the data, the input data, which is what I just showed you, which was in data, Hurricane Dorian, ABD. We need to pass a cover file. Now, this is a bit technical, but if you look in GitHub, it will tell you exactly what it is. I don't want to get into the specifics because it's not instructive. We need to pass. We need to tell where is the pre-trained model that we want to use. Now, as I mentioned, is this neat full-XView epoch 75 is simply the name of the file which contains the pre-trained model that we're going to use for this. I'm going to tell it where to save the output. Where do we save it? Hurricane, ABD predictions. And then two other parameters, it doesn't matter. Meta tiles, keep borders. Just some aesthetics of the predictions. So, well, it's a bit of a long command because I need to specify what to take from where and where to put the output, just to make it like more flexible that you can use it however you want. But it's just one command. And now what is happening behind the scenes is that it is checking which images I have available. It's taking many little pieces of those images, and each of these images is passing to the model to detect if there are buildings in that little piece or not. After we have detected, the output of the model is actually another image, which simply tells me are there buildings here, yes or no. And then in a next step, we are gonna translate that into actual buildings, so into a vector file that you can visualize with GIS or with any kind of mapping service. So as you can see here in the bottom, yeah, it's starting to predict. It's using 4 GPUs, and yeah, it's going on. As you see on the right side, the expected execution time is 6 minutes. So that's how long it takes to map, or even less, 5 minutes something. That's what it takes to map this whole area. And at the end of it, yes, we will have this yeah, we will have predictions on the buildings. As I mentioned, the first output will be an image. We need to vectorize it. Now, I'm not going to wait until this is over. It's just we should just wait 5 minutes. I don't think it's necessary since I already ran this before. So I just killed the process. nothing magical. I just stopped it. As we already have the output, so we can just use it. As I mentioned, we need to then create this vector file that can be used in mapping. And for that, we need to vectorize the output. I need to tell it where is the data that I just produced with the model just produced, predictions. I need to tell it the type, it's a building. I need to tell the where we want to store the output. In this case, it would be a vector file. Let's call it buildings.geojson. And again, it needs a config file. So now I'm just translating the output of the model, which again are images, into an actual vector file, which can be used to make maps, basically. Just takes a minute, so this we can wait. And that's pretty much it. So that's what you need to get the buildings. There is a bit of setup required, but yeah, we think it's relatively easy to reproduce as a workflow. Voila, it's over. And now I save the output in a GeoJSON, which I called buildings.geojson. And of course, for the purpose of time in this tutorial, I'm just going to show you the output, which I prepared already in my presentation. Yeah, this is what you got from the building detection part. You see that we got the buildings in black. I think this is a good example because it shows you both how good it can perform. In some areas, you see that it works very well. You see all the little houses in the residential neighborhood, but you also see on the right-hand side, I don't know if you see my mouse, but I mean here on the right-hand side, it does not see all the buildings behind the cloud, or of course, it has a hard time seeing buildings behind the cloud. And this is, as I mentioned earlier, a fundamental limitation. If your images are covered with clouds, you don't see buildings behind in optical images. So yeah, that's another fundamental limitation. But on the pieces of the image where we don't have clouds, it performs relatively well. And you see that most of the buildings are correctly mapped. So now we have our buildings. We can do the damage classification, right? Which might be another task in the case of Hurricane Dorian. I guess this was one of the things that was that we needed to do in the first place, right? Understand the scale of the damage. So the next step would be damage assessment. How we do the damage classification. Yeah? Again, the concept here is that we take as an input the satellite images, the location of the buildings, which is what we just produced, and we classify the damage at the building level. So now I'm going to go back to my, to this. I'm going to change environment, like it's not important for you guys. It's just a small detail. And again, running the damage classification model is one step, one command. We don't have it really executable. It's just we need to run a Python script. On the Py, again, we need to pass a bunch of parameters. The name of the run, this is simply the name of the specific instance in which we execute the code. Data path, so where do we keep the data that needs to be processed? Hurricane tutorial. The model path, that's the which pre-trained model you want to use. So is called best model, right? The checkpoint that's what you want to save the logs of this particular run. So let's just say Hurricane Dorian tutorial Calarius runs. Output type. Classification. Now, if you see on the documentation on GitHub, you see an explanation for each of these parameters. I don't think now it's necessary to go into, to explain why we use every single parameter and how, but on GitHub you find relatively decent documentation on this stuff. Now, as I mentioned, the damage classification part is even faster than the building detection. So I think, it should be very quick, at least 10 times quicker. So like it should be done in a minute if everything goes as expected. Now I'm a bit worried that the curse of the tutorials, that when you do a live demo, then nothing works. So then, the usual launch of an app is always but yeah, basically now, it's done, completed in 48 seconds. So we just produced now the predictions on the damage classes for each building, and we saved it somewhere on this machine. Now again, for the purpose of this tutorial, I already took the output and put it in my presentation so that we can have a look together. Because again, I lost the slide. I always do that. Where were we? Here. So that's what we got. That's the output of the model. In red, you see the buildings which are moderately damaged or completely destroyed. And in green, you see the buildings which have no or minor damage. So that's the kind of output that you get. As I mentioned before, since we don't see buildings where there are clouds, we're not going to classify damage there because we don't know if there are buildings and where are the buildings. So that's again, it's just a consequence of what I mentioned earlier, that we don't see buildings there. Now let's inspect the output because that's always useful to make sure that the model is performing as you expect. It might not be perfect, but if you have a quick inspection by hand, you see if the output makes sense or not, right? Before actually, especially if you're in an emergency situation where you have the responsibility to providing estimates, I think it's very important to take a second and manually check the output of these, just to make sure that everything went as expected. Now, I just took a couple of images here. You see in this one, on the left is the post-disaster image, and on the right is the classification. Now, here it seems to go pretty well. So what is green is pretty much in good shape, and what is red is pretty much in bad shape, except maybe this big building here, which somehow seems damaged. But for the other, it seems to do a decent job. The same here. You see this is a residential neighborhood. You see mostly buildings damaged, and in fact they are. Maybe one or two of them are a bit questionable. Like this one is damaged and maybe it should not be. Now this one seems okay. This one actually damaged. So again, it seems pretty much okay. But always good to check. Now I also took an example in which the model failed completely, and it's this one. Like you see that here, probably because it was such a mess of debris and whatever pieces of houses that it's simply impossible I mean, I guess the model just got completely confused because there is nothing that you can even recognize as a house. So you see here that the model, failed completely. Here in the center, you have all these blobs, which should be buildings, which are classified as not damaged, but we know that it's just a mountain of debris. So yeah, this is an example of an extreme case in which the model can get confused, and you should be aware of that. Depending on what how your use case is. Just, to manage expectations. And then that's another image. This is a residential area in the north, which somehow seemed less damaged than the rest. So I just wanted to check if that's actually the case. And indeed, you see many more green buildings here, but they do seem to be indeed in good shape, at least from what you can see from the top. So yeah, at least also in this area, the model is actually working. So that's it. If you checked your output and you are relatively confident that it makes sense, then that's you did what you need to do. And then you can use this data to provide estimates, to make a map, to provide estimates on the damage, and to use this in your emergency operation. However, this might be suitable. So conclusions, automated mapping and damage assessment can be a useful tool in emergency response, given everything that I mentioned at the beginning. So given the specific scope that we defined, it is faster and more often available than current methods. With this, I mean that you know that as long as you have a computer, you can run this anytime that you want. Well, sorry, a computer and a satellite image, important to mention. But if you have both, then you can run it anytime. You don't need to set up a task in hot. You don't need to wait for people to pick it up. It's always available, and it's way faster. That's the main advantage of this. Everything is open source. So everything, the code, the models, the instructions, everything is open. It's on GitHub. It's on Docker. Even the last item that I mentioned here is the example in which we had this distributed computing in Azure to basically parallelize the process on many machines and make it even faster. Everything is open source and documented. So I really encourage you to check out these resources and try it out by yourself. The way I really wanted this tutorial to show you that what it means concretely and that it can be done, and would like you to feel that yes, you can also do it. I hope you were not scared too much by the jargon. I don't know if you're not used to certain words that I used, like some technical jargon about Azure stuff, but following the tutorials, I'm pretty confident that you can do it as well. Okay, we would like at least every national society to be empowered with this kind of technology, being able to run these analyses by themselves if they need. A few real use cases just to leave you with the correct perspective that this is not only a theoretical exercise, but it has been used already in emergency response. Last year in 3 cases for the mapping case in the Philippines, Guatemala, and Zimbabwe, and the damage assessment for the explosion in Beirut. Was the first time that we actually delivered a damage assessment using this technology. And you can check the output. Actually, we put it on HDX under our organization page, Netherlands Red Cross. So again, you can check the output there of what we did with this technology. That was it from me. Thank you very much for attending. I was very happy to see so many of you connected. And if you want, if you're curious about this, if you have specific questions, if you want support to test it, to run this on your own machine, this is my contact. We're always available to support. Thank you. So now I've been speaking for quite some time to a bunch of letters and pictures. So if someone would like to turn on the video, maybe share something, questions, I don't know, opinions, point of view. What do you think about this? Would you consider using it? Maybe now it's time to get it a bit more interactive. Suleiman.
Okay, sorry, it's me again. So I'm just wondering, since you're asking for questions, like if your model is trained on certain images in the past, and then like you end up in different scenarios where you have tents, for example, and like your model is not used to it. Is there a way you can train the model again on some images, doing it manually, and then like use it, or shall you give up? Just an imaginary scenario if this case happen, and I hope we never use it. We always try to avoid disaster, so yeah. So basically, I hope my question is clear. If not, I can re-explain it. Over. Thank you.
Thank you, Suleiman. Yes, it is very clear, and it's a very good question. So what you would want then is some sort of workflow within OpenStreetMap in which people can actually label damage, and then this can be then consumed by the model to retrain the model with the new data of the specific emergency, and then we can improve on the predictions based on the data that in the meanwhile has been labeled by people. Now, this is a great idea, and we're actually talking with the hot OSM to get this done, like to have damage assessment crowdsourced on OSM, not only to improve the model, but just to serve the community with such a thing, with the concept of damage assessments. And we will get there, but we're not there yet. So at the moment, we don't have a practical solution to retrain the model live on a new emergency. I'm just going to be honest. But what we explored in this paper is exactly the one that I mentioned here. Let me click it. What we explored in this paper is exactly which kind of performance would you expect from this model in a new emergency, depending on the type of disaster and other characteristics. So this is just to give that's what we have at the moment. We can only say if we think it would work or not, but we don't have a workflow yet. But we will get there. I'm confident.
Great, thank you. Thank you so much again, and it was very helpful. Thank you again.
Thank you, Natalie.
Oh, thank you. This is what I've turned on my video. Thank you for that great presentation. It's really interesting and the development from what I'd already heard about this work that you're doing. It's great. My question is about the images and the range of acceptable images. You already spoke about off-nadir images and where they're affecting things and the conditions on the ground. But I'm wondering also about different resolutions, different times of day, even perhaps how extensible some of these models might be to aerial imagery rather than satellite imagery, and just I guess how wide the different types of images could be that the work you've done already might cope with.
Yeah, so in my experience, neural networks are quite sensitive to changes in resolution. So I don't expect the same model to work well with, say, drone images, which are very high resolution. This said, this XBD dataset that I mentioned, we also chose it because it combines data from different sensors, and it is already data images with a resolution between 0.15 meters per pixel and 0.5. And within this range, basically all satellites which provide high resolution optical images are within this range. So if you train a model with different examples within this, in terms of resolution, you cover it pretty much. So when it comes to satellites, we believe that it's robust enough. With drones or other aerial images, it is likely that it would be a different model. It can be trained. However, in the way we move to satellite, the way we chose the way we think about it, and that's why we only talk about satellites, is that if you want the drone imagery, usually you lose the speed because drones, not only they need an expert team to fly them on the ground, but they also take time, especially if you're talking about 10,000 square kilometers. It's going to be weeks to get it by drone. So you lose, and then I don't see the advantage of automating this if anyway, it's a process that takes weeks. What is this? But it's the same technology can be used there in principle.
Okay. Yes, I was thinking more about the aerial imagery, like some of the Defence Force planes might capture and things, rather than necessarily the lower down drones. But great, thank you for those insights into the range of image.
Neil?
I'm a little bit afraid to ask because I came to the end of the presentation. You may have covered this already, but I was wondering if you had an accuracy score in terms of this technique compared to the accuracy of volunteers looking at the satellite images through HOT, for example, and then I was a little bit curious about which machine learning model was used, whether it was kind of a neural net or support vector machine combination. If you went into that, or if you have an answer.
Sure. About the performance. Here. So the performance that we report for the mapping part, that's 10% of building missed. That's with respect to ground truth. That's well, I'm not going to specifics, but that's as good as it can get. And usually there are not detailed studies on the accuracy of OSM, but I would expect it to be between. So this would be 90% accuracy. OSM would be anywhere between 90 and 100, 95, 96. That unfortunately they're not. I don't know at least of studies to quantify this, but we're talking about this is the difference more or less. Okay.
So with HOT, you're thinking or if I understand you correctly, it's about the same accuracy as HOT?
Yeah, about this exactly. For some people, 5% difference in accuracy is huge. Depends how you feel it. The difference, I think, it's between 5 and 10% of accuracy. Actually, between 0 and 10%. It might be even more or less the same. When it comes to damage classification, that's a bit more complicated. So when I say misclassified, I mean, so what we compare against when I calculate the model performance here is the damage assessment done on satellite images by people, by volunteers. And we take that as a source of truth. Now, this has not been confirmed by field assessments. So it is very hard to find data in which you have both the damage labeled in the satellite image and a data point from a field assessment that confirms or not the particular damage on that particular building. So that is definitely the next step to validate all this technology, is to get this data and do this kind of studies. At the moment, as far as I know, no one has produced these data sets to do this kind of studies. We can only compare damage assessment on satellite images done by machines or by humans, but on the same image. And that is the performance that I talk about here. So that's how they differ to each other. I don't know what is truth. And probably to know the truth, I would need a field assessment or something like that. So that's what we got. But again, to put it in perspective, even if there is some difference, this is really meant for the very first days after an emergency. Okay, so this is not meant to be accurate. This is meant to be fast, to provide an estimate. So. In my mind, for the use case here is not really so much dependent on reaching a very high accuracy, if you know what I mean. I think very often an estimate with a 30% accuracy is much better than anything else available if you get it 24 hours after the disaster, when usually you don't know anything. I don't know if people agree with me on this statement. Maybe it's a bit bold, but
I agree. I'll just put that out there. But then the second part, so is the model's a pseudo-Siamese network? I have to confess I don't know that one.
It's a neural network. It's it simply means that it's two convolutional neural networks. I don't know if you're familiar with those.
Yeah, I'm familiar with those.
Okay, so a pseudo-Siamese network is basically you take two CNNs, two convolutional neural networks in parallel, you make them process two images in parallel, and at the end you chain them with a couple of fully connected layers, and you do classification at the end. That's what called pseudo-Siamese, is because you have two identical networks, and at the end you compare the output of the two. And in this particular case, one network would read the post-disaster image, another network would read the pre-disaster image, and at the end you classify the interaction on the features extracted from each image. It's a little bit technical, but
okay, thanks.
on GitHub you find a better explanation than what I gave now, which is very bit confused. So you can have a look there. Teamwork?
Hello, can you hear me?
Yes. Hi.
Right. So I have a question regarding the model itself. So I assume it should be in the paper and on GitHub. This is first question regarding why the specific choice of architecture. Have you tried other architectures and what failed probably? And is it currently kind of state-of-the-art a selection of model for this specific problem? And second question: what's your plan for the model, and are you planning to have it, for example, as like serving with API, so that, for example, people could put don't need to set up Docker. Docker is nice, of course, but like so that anyone could have this service to put the files and get results and analyze it from that perspective. So two questions. Thanks.
Thanks. So no, the choice of the architectures, to be honest, was a compromise between. So let's say we took the family of models, so CNNs and small variations of CNNs, which we know works the best, work relatively well for the problem. And then which among the best architectures, we basically chose the ones which were easier to implement. It was a compromise between complexity and performance. The reason is that there is so much research in computer vision that if you really want to take state-of-the-art models, they very quickly become a behemoth, like super complicated, because it's maybe 10 different networks, and then you do ensembles, and then you weight the outputs, and like operationally, like to make it into something, to make it into something that you can easily set up everywhere. At least for us, we decided not to go there. So it's not exactly state-of-the-art, but it's close to the state-of-the-art. And in the paper, we argument a bit why we chose this architecture and what else is out there in the market, if you want to do more, But yeah, it was not really, I would say, it was not too much the focus of this. And then next, about the program for the future. So the main so at the moment, we don't plan to provide this as a, like to simply open an API and then you can send a request with an image and it will run it for you. For two reasons. One, because the resources cost. So I mentioned here that to cover 12,000 square kilometers, it costs 24 euros, which is not insane. But then if we provide it as a service and then we get 10 requests per day, then the costs quickly become unsustainable for us. So we cannot afford, we could afford it to provide as a service with an API, but then, because we will never make people pay for this, right? Because we provide emergency support. So we need to do it free. provide it for free, and then it quickly becomes very complicated with the costs. If there is really becomes a tool used by everyone. However, there is another also important reason why we don't want to, especially damage assessment, we don't want to provide as a service, which is damage assessment can be very political. They can be very sensitive, okay? So in some emergencies, damage assessments, in some countries, the government decides that they're going to conduct the damage assessment, and no other agency, for instance, might be allowed to share information in that sense. So we want to avoid putting the local Red Cross or any other national society working there in the awkward position of using data which is not really the case to use. So having these in your hands also means that responsibility on whether to use it or not, and the output sits on the data user. So it's a bit more, yeah. Yeah, it's let's say we assume that by having this set up by yourself, you also go through a bit more of the process on how it's done. It's not just clicking a button and then you produce a map and then there is our name attached, and then this can be misused by people, governments in any case. But this is, I would say, it's a separate discussion about data responsibility and how to use this. Happy to talk about it, but not sure if relevant for this tutorial.
Thanks for explanation. Well done.
Thanks. Anyone else? Don't be shy. There are no stupid questions, only stupid answers. And that will be on me, so you don't risk anything.
Hi, Jacobo. Thank you very much for the presentation. I've been a hot volunteer for quite some time, and I've done a lot of manual building tracking in JOSM, and it gets old really, really fast. So if I feel like this is maybe for a much bigger scale things, would you have any pointers or information you could direct me to if I wanted to start importing data sets to or building outlines to OpenStreetMap from a much smaller area with a higher accuracy? And feel free to ignore the question because it's a bit of off topic.
No, it's a good question. That's also what we're discussing with HotOSM. I guess you are aware of Rapid or RapidID. That's a tool set up by Facebook. The Facebook released these AI predictions on roads, and you can import that in your task and validate that within OSM. Now, what we are discussing with them is, can we do the same for buildings? So once we produce this automated mapping, can we just import it as in RapidID and use that as suggestion for the mappers? I don't know if that's what you meant. I guess that's how I understood what you were asking.
Yeah, that sounds good. I'll definitely check it out.
It would be within RapidID. At the moment, it's not there. It's only roads. Buildings will be there. I think it's timescale is like a couple of months. I hope. Well, no, a couple of months to get because we're setting up a test earlier. I don't want to make promises, but let's say within 1 year, I hope these will be there to be used by mappers.
Okay, great. I'll start following your GitHub repo so I know when you publish it. Thanks.
Oh, follow me on GitHub.
One more question, just regarding the data. Is it only Maxar for data download, and what is the resolution for imagery?
So it's at the moment is only Maxar for automatic download. You can you can use others, but then you have to input by hand. Where is that automated download? Yeah, load images. Now it's only connected to Open Data Max or Open Data. So yes, the resolution in Max depends. They have different sensors. So I think it's between 0.3 and 0.5. Yes, because the only ones that have 0.15 is Planet, if I remember correctly. So Max says between 0.3 and 0.5.
And does the accuracy changes on change of resolution and how the model reacts to it?
That is something that we did not study in the specific, because in the paper we were mostly focusing on the type of disaster, the geographical area, not on these details of the model. So we do think that resolution will affect a little bit, but not dramatically. So I don't expect a major difference in performance between 0.3 and 0.5. If you go above 0.5, then yes. But no, I don't think this would be a major role. Just an intuition. Although, again, I don't have strong experiments to support it. Just my experience.
And last question, thank you. Does the output providing probabilities of how certain this building could be damaged or not, and kind of this additional data?
Yeah, in the classification part, yes. I didn't show you because we don't discuss it. But if you want to do more detailed analysis, yes, you can also get probabilities. That's possible. Because at the end, classification is always a softmax layer at the end. So you can the input before is always a probability that then gets sliced. So yeah, you can always get probabilities. Suleiman?
Just another weird question. Is there a possibility to have to include the size of the buildings being damaged in the assessment as an indicator when you have a large size? So the map is taking them as the number of buildings. The model is taking the number of buildings, right?
Mm-hmm.
But what if a building is very big and then the other one is a very, very small building? So yeah, I don't know if I'm okay. Let me put it in other words. The map is counting the number of buildings, right, and doing the assessment for the damage. The model, sorry.
The model is taking, when I do the damage assessment, I take the image of each individual building and I classify that. It doesn't matter if the building is small or big. I just take the image, whatever that is, it can be big or small, and I classify that image.
Okay.
So,
yeah, I'm just having an idea, if the building was, if there is a way you can, I'm just forgetting the word in English. Just give me a second, sorry.
Is it kind of like scoring the level of damage by the size of the building? Is that what you're...
Yeah, exactly, yeah. This is what I'm trying.
Okay. So basically, okay, it makes sense. So you report the damage in terms of total square meters, not in terms of total number of damaged buildings,
yes, exactly.
but total number of...
That's what I was trying to say. Yeah, sorry.
Yeah. Cool. It's a good idea. I guess it depends on your use case. I mean, all this information is there. You can, with any kind of GIS software, you can extract this information from the output. You don't need to do anything fancy with code. I would say it depends on the use case. If this information, for instance, let's take an emergency where they need to buy roofing material, right? And they need to know how much roofing material do we need. In such a case, I guess square meters is a better information than the number of buildings, because it tells you exactly how many square meters of roofing material you need. So if on the other hand you're using this information to make an estimate on the number of displaced people, then the number of houses, I think it correlates better with the number of households than the square meters. So yeah, different information, but all can be extracted from this output with GIS software.
Yeah, GIS is a good idea to do this. Yeah, thank you.
Okay, I see we are almost out of time. If there's any last quick question. Data scientist 2. Yeah, identify yourself.
Yeah, but in fact, my question is not on the data science side of it, but more on the implementation. Maybe if you can tell us some, yeah, I don't know, experiences, because yeah, of how had been the implementation of this in a well, yeah, a specific experience of the use of this and how it was. For example, now you were given an idea of how it could be used, but I don't know if you have some examples of how it has been used.
Yeah, well, I can go. So these are the use cases where we used them. It has been, yeah, so the mapping, it has, like, in terms of implementation, is relatively straightforward. The humanitarian world already knows, already has a lot of many processes that rotate around maps. We need maps to do this, to do operations, to make a plan, to maps are used by, yeah, but by many people for many processes. So in this sense, there is nothing special about this. Instead of making a map with OpenStreetMap, we make a map with what the model produces. So it's the implementation in terms of in the humanitarian processes, what is quite straightforward. Now, in terms of, I don't know if you meant DevOps, so deployment, implementation in terms of software, in terms of having it run on a machine.
No. It was the basic version of it. So it was okay. Yeah, maybe because you said that you extract from here a JSON file, but then probably it has all the polygons, and with that they are going to map it, and then the whole humanitarian process goes. So yeah, I think that was the question. Maybe if there was some other thing, but yeah, I think that was the question I made. Cool.
Damage assessments are a bit more tricky because, as I mentioned, in some contexts they can be political. So the Red Cross does not have the mandate to do that and cannot do that. In other places they can, and they can share this information with the government. In other places they can, but they can only use the information internally. So the processes with damage assessments are a bit less clear, at least in my understanding. Maybe there is someone with more experience than me in the call that can clarify. However, this kind of data, I think it can be, again, consumed directly to make maps or to make estimates of numbers. And then the complicated part, I would say, is to figure out if and how we can do damage assessment in the specific operation. That has nothing to do with models and computers. That has to do with humans, which are sometimes more complicated.
Good, nice, thank you.
Cool. So I'm going to share the presentation in the chat for you. So I'm going to stop sharing. And I'm also going to stop recording here.